Hello, this is the refrigeration presentation from Team 2 for the Mechanical Engineering Systems Lab at Georgia Tech. This team is comprised of Adriana Bays, Brooke Aroglu, Aiden Perez, and Bowen Xiang. A newly developed cooling system by Machine Chillers Incorporated can cool an object using a vortex tube and air as a working fluid. The Burdell Incorporated team has been tasked with modeling the system in order to determine its capabilities and ideal operating conditions. The goal is to characterize the vortex tube input and output properties, the heat transfer at the load, and the compressor's ability to pressurize the system. Station 1 of the system measures the compressed air into the system. A heat exchanger between stations 1 and 2 cools the air to ambient temperature. Pressure variation is then removed between stations 2 and 3. Station 4 creates both hot and cold outputs. And finally, Station 5 measures the flow of outputted air and vents the air. For week 1, we ran the system at different voltages until steady state, where we collected offset data, temperatures, pressures, and mass flow rate. Then, we measured the dimensions of the block load, where we used that to calculate the theoretical insulation resistance. Next, we calculated the uncertainty of the total energy transfer between the air and the resistance, experimental and theoretical. Finally, we characterized the steady-state relationship between the motor setting and system pressure, vortex tube input/output properties, and heat transfer at the load. This graph shows the relationship between the input voltage and the pressure from the compressor, which can be modeled as a quadratic relationship, curving downwards. At high input voltages, the pressure seems to start to plateau slightly. This equation can be used to calculate the voltage needed if we want a desired pressure. Here, we can compare the temperature at the vortex tube with the pressure from the compressor. The temperature of the cold side of the vortex tube decreases with an increasing pressure and can be modeled with a linear relationship. Conversely, the temperature on the hot side actually increases as the pressure increases and can be modeled as a linear relationship. Both of these graphs have ellipses that represent the uncertainty in our data. Next, the mass flow rate versus pressure at the compressor can be modeled. The plots indicate that the mass flow rate increases as the pressure increases for both the hot and the cold sides. The cold mass flow rate increases linearly. However, the hot air mass flow rate starts to plateau at a higher pressure and can be modeled as a quadratic relationship. This is most likely due to the compressor having to provide more work to convert the air into a working fluid at these higher pressures. Here, we can see the relationship between T3 and the ambient temperature for each voltage. We see an increase in ambient temperature as the voltage increases, which could be due to residual heat transfer to the surrounding air from the system as it continues to run. The percent difference seems to stay around the same at around 0.5%. Thus, the modeling assumption that T3 is equal to ambient temperature can be supported. Here, we see how the pressure at either side of the load changes with the voltage. For our modeling assumptions, we assume the pressure at each side of the load was equal to the ambient pressure. However, we see a large percent difference in pressure around very low voltages and very high voltages. This means that the pressure drop across the flow meters is not negligible and needs to be taken into account.
So moving on to the results, here we calculate the theoretical work done by air as well as the thermal resistance. All the data collected during week 1 is under the steady state assumption, where the work done by air is equal to the work out at the load. We calculated the theoretical work done by air by taking the thermal resistance, 1 over it, and multiplying that by the temperature difference between the ambient and the actual load. And then the theoretical thermal resistance of the load was calculated by taking the length of the insulation and dividing that by the thermal conductivity and then the area of the insulation that's within contact with the aluminum block. So to actually calculate the actual the thermal resistance, we used the thermal conductivity of styrofoam, the average thickness, and as well as the contact area between the block and the insulation. Multiplying all those through, we get a thermal resistance of 22.072 Kelvin seconds over joules. And then that insulated thermal resistance value is then multiplied by the experimental data collected in order to get the theoretical work done due to ambient. So for the actual experimental calculations of the two, we use the assumption where the work done to the air is due to the specific heat capacity multiplied by the mass flow rate multiplied by the temperature difference across the load of the air. And then the thermal resistance is taken by dividing the temperature delta across between ambient and the load and dividing it by the actual heat transfer due to air. So taking all the equations from above and all the experimental data collected between 0.5 and 2.5 volts, we get the theoretical and the experimental thermal resistance and heat transfer. It's clear with the theoretical, with increasing voltage, there's an increase in the total heat transfer. But experimentally, that breaks down after 2 volts, which the causes will be explained later on. So here, we've gone and plotted the load temperature delta versus the theoretical and experimental heat transfer loads. You can see here clearly that as the load temperature delta increases, theoretically it follows a very linear trend due to the insulative resistance staying exactly the same. But experimentally, it's obvious that it breaks down after around 1 volt, the relationship between the two, and then really breaks down heavily after 1.5 volts, where the heat load suddenly goes negative, or otherwise the temperature decreases as the air flows across the load.
To determine whether the energy transfer rate between the ambient and air are the same as steady state, the uncertainties must be known. These are the equations used in the uncertainty analysis. This table shows the uncertainty values of the energy transfer rate of both the air and ambient. It also shows the uncertainty of the experimental insulation resistance and the discrepancy between the energy transfer rates. It is notable that the uncertainty of the insulation resistance is very high, especially for the 2 and 2.5 voltages. Additionally, the energy transfer rate of the air is negative for these voltages. This is most likely due to the T5 and T4C temperature readings being so similar for these voltages. The negative Q air is due to the T4C being slightly greater than T5. This does suggest that the data should be retaken as the Q air should not be negative. This plot shows the uncertainty between the energy transfer rates of the air and ambient. Since there is overlap between the two values, they cannot be told apart from one another. This means that the system's steady-state assumptions are valid for this voltage. This table shows for what voltages the uncertainties overlap. Since the discrepancy between the energy transfer rates is less than the uncertainties for the 0.5, 1, and 1.5 voltages, the assumptions associated with the system at steady state are correct. These assumptions are not valid for the 2 and 2.5 volts. It should be re-emphasized that the results are not trustworthy due to the closeness of the T4C and T5 values, and the data should be retaken.
Our plans for next week include recalibration,
modeling the transient cooling of the
aluminum block while it is exposed to both the compressor and the building air, and of course we will be careful to allow the block to return to room temperature. We will then calculate Q.load, Q.air, Q.ambient, and of course Q.discrepancy, and our job is to determine how these experimental material properties match up to published values. Our plan for next week includes recalibration, modeling the transient cooling of the load, the aluminum block, while it is exposed to both the compressor and the building air. We will be careful to allow the block to return to room temperature, in our case heating it up with a heat gun. We plan on calculating Q.load, Q.air, Q.ambient, and of course Q.discrepancy. And we are as well interested in how the experimental material properties of the load match up to the published values. As plainly demonstrated before, at lower load temperatures, the experimental heat loads are much closer to their respective theoretical values. The experimental heat load and thermal resistance are negative at 2 and 2.5 volts. This could be due to our model's assumption being off. Alternatively, it could be that the theoretical Q.amb is over-predicting heat transfer in the 0.5 to 1.5 volt range. We believe it's a mixture of both, but likely due to how the thermal resistance is dependent on conduction and convection, not just conduction as assumed. It leads to a real thermal resistance higher than expected and a lower heat load.